You're not made of particles. You're made of ripples, trembling on invisible oceans that fill every inch of empty space. Scientists just confirmed it. The electron in your finger, the light from your screen, even the weight holding you in your chair, each one is a vibration on a field that is here long before you were. Tonight we walk inside the Higgs ocean, touch the vacuum that hums in the dark, and meet the quantum ghost hiding behind every atom. If this kind of calm, deep dive helps you drift off, hit subscribe and settle in. Close your eyes, we begin. For most of the last century, physics told us a simple story. Everything you see is built out of tiny solid balls, atoms and inside atoms smaller balls, electrons, protons, neutrons. Smash them hard enough and you find even tinier balls inside. The word particle itself comes from the Latin for small part, and for a long time nobody questioned the name. Then something quiet happened in the laboratories. Slowly, over decades, the balls stopped behaving like balls. An electron fired at a screen would land in one spot, yes, a single dot, like a pebble thrown at a wall. But fire enough of them, one by one, and a pattern appeared. Stripes, ripples, the kind of pattern you only see when waves pass through each other on water. A single electron, travelling alone through an empty chamber, somehow knew how to make a wave pattern by itself. That was the first crack. The second crack came from a young British physicist named Paul Dirac. He was trying to write an equation that described how an electron moves when it's also going nearly the speed of light. The equation worked. It predicted the electron perfectly. The trouble was that the same equation also predicted a second electron identical in every way, except with the opposite electric charge. A mirror twin. Dirac stared at the math and realized his equation was not describing one lonely particle. It was describing a whole field, and the particle was just a small wrinkle in it. Here is where the story shifts quietly, forever. Picture a calm lake at night. You cannot see the water itself in the dark. You can only see a ripple when something disturbs the surface. A fish jumps, a stone drops, a ripple appears, moves for a while, then fades. You point at the ripple and you say, "There is a thing." Then the thing is gone. What was it made of? The water. The ripple was never a thing. The ripple was a behavior of the water. That is what physicists slowly realized about electrons. The electron is a ripple. The lake is something they started calling the electron field. And the field, stunningly, fills the entire universe. Every cubic inch of space, inside you, inside the sun, inside the empty black vacuum between galaxies, contains the electron field silently waiting. Disturb it anywhere, and a ripple appears. We call that ripple an electron. The old picture, the one with tiny billiard balls flying through empty space, quietly died. In its place came something stranger. The universe is not a container filled with tiny things. The universe is a set of invisible oceans, layered on top of each other, and the things we call particles are just the ripples each ocean happens to be making today. Scientists resisted this idea for years. It sounded too philosophical, too poetic, too unlike the neat pictures in textbooks. But the experiments kept agreeing with the ripples and disagreeing with the balls. One test after another, one decade after another. By the time the last doubters gave up, a deeper question was already waiting for them. If every electron is a ripple on the same endless ocean, then every electron everywhere is connected to every other electron. And if that is true, something very strange follows about the room you're sitting in right now. Reach out, touch the air in front of you. You feel nothing. A little warmth, maybe the movement of a breath, and that is all. Your hand passes through what seems like perfectly empty space. Now hold that feeling, because physics is going to take it away from you. The space your hand just swept through is, according to quantum field theory, one of the busiest regions in the universe. In every cubic millimetre of that apparently empty air, there are at least a dozen invisible oceans laid over each other, all trembling at once. The electron ocean, the photon ocean, which carries light, the quark ocean, which builds the inside of every atom in your body, the Higgs ocean, which gives things weight. Each one fills the whole room. Each one fills the whole planet. Each one fills the whole cosmos. They are not mixed like soup. They sit in the same place at the same time, like different radio stations broadcasting through the same air. Your hand passing through disturbed all of them a tiny amount. You just did not see it. A researcher at a university in Maryland once put it this way during a public lecture. She said, "Imagine that the universe is a single musical instrument with a dozen strings. Every time a particle appears, one of those strings plucks. Every time a particle disappears, the string quiets back down. The strings are always there. The music only happens when something makes them move. That is the quantum field picture in one image. Here is the part that makes people pause. These oceans are never fully still. Even at the coldest possible temperature, colder than anything ever measured in deep space, the fields refuse to stop moving. They shiver. Physicists call it zero-point motion, because zero is supposed to mean nothing, and yet there is still a trembling left over. An experiment first performed in the 1990s made this visible. 2 metal plates were brought close together in a sealed vacuum chamber. All the air was pumped out, all the light blocked. According to old physics, nothing should happen. Instead, the plates pulled toward each other. Something in the empty gap was pushing them gently together. That something was the ghostly trembling of the fields between them. The effect is tiny. Across plates the size of a postage stamp, held about 100,000th of an inch apart, the pull is only a fraction of an ounce. Still, it is real, measurable, and repeatable. Any physics lab on Earth can check it. That little force is your first direct evidence that the room you are sitting in is not empty. It is full of something invisible, restless, humming at the edge of existence. Which raises an uncomfortable thought. If every point in this room contains a field, and every field is trembling, then you, the body reading these words in your head, are sitting inside a silent storm. You cannot feel it because you are made of the same storm. Your cells, your blood, your bones, every atom of you is a pattern of ripples on those same oceans. The emptiness you always believed in was never empty, and the particles you always believed in were never particles. To see what they really are, we have to look at one of the strangest experiments ever performed. Picture a wall with 2 narrow vertical slits cut into it. Behind that wall, a second wall, smooth and white, ready to record anything that hits it. Now imagine you have a machine that can fire a single electron, one at a time. You aim it at the first wall and pull the trigger. The electron flies through, goes through one of the 2 slits and lands on the back wall with a small flash. You mark the spot. You do it again, and again, thousands of times. If the electron were a tiny ball, the pattern on the back wall should be simple. 2 bright stripes, one behind each slit, matching the paths the balls would naturally take. That is what common sense says. That is what every scientist expected the first time this was tried. That is not what happens. What appears on the back wall, after enough electrons have hit it, is a series of many bright stripes with dark bands between them. It looks exactly like the pattern water makes when two ripples meet and interfere, lifting each other in some places and cancelling out in others. A single electron fired alone through a wall with two holes produced a wave pattern. The only explanation that works is unsettling. Each electron on its way to the wall is not a ball. It is a ripple on the electron field, and the ripple is wide enough to pass through both slits at the same time. When the ripple reaches the back wall, it collapses into a single dot at one spot, and that spot is chosen with probabilities that match exactly what a spread-out wave would predict. Here is where the experiment gets deeply strange. Scientists wanted to catch the electron in the act. They set up a tiny detector at one of the slits, something that could whisper. Yes, the electron went through this one. They fired electrons again. This time, the wave pattern vanished. Only two plain stripes appeared, one behind each slit, exactly like balls would make. Just by looking, they changed the answer. When nobody checks which slit, the electron behaves like a ripple passing through both. When somebody checks, the electron behaves like a ball passing through one. The act of measuring, the simple effort to know, reshapes the result. A physicist in Vienna repeated this experiment with larger and larger objects. First with electrons, then with whole atoms, then with molecules made of dozens of atoms, then in the last few years with molecules containing thousands of atoms. Every time the answer was the same. Left alone, they ripple. Watched, they become things. Something very old died in this experiment. The belief that the world is made of solid objects with definite positions, whether or not anyone is looking. The ripple is the truth. The dot on the wall is only the moment the truth is forced to pick a place. This is the first real taste of what a quantum field is. It is a set of possibilities, spread out through space, waiting. A particle is what happens when those possibilities get collected into a single visible event. If one lonely electron can be a ripple that fills a whole chamber, a deeper question now waits. How big, really, is that ripple allowed to be? Imagine standing at the edge of a perfectly still pond at dawn. You drop a single pebble into the centre. A ring of ripples spreads outward. The ring grows, reaches the far shore, bounces back, fades. The water was there all along. The pebble just gave it a reason to move. That is very close to what happens when an electron appears. Somewhere in space, something disturbs the electron field. Maybe another particle collides with it. Maybe a photon of light hands over a little energy. The field responds with a ripple spreading outward in all directions like the surface of that pond. The ripple is the electron. Here is the thing that breaks human intuition. The ripple does not sit in one place. It is genuinely spread out. A careful measurement of a slow-moving electron shows that its wave can easily be wider than the atom it is part of. Inside a hydrogen atom, the electron is not a tiny ball circling the proton. It is a fuzzy cloud, a standing ripple surrounding the center like a soft shell. A graduate student in California once tried to explain this to her grandmother at dinner. She took a drinking glass, filled it with water, and tapped the rim with a spoon. The water shivered in a pattern. She said, "Grandma, this is how the electron sits inside the atom. It is not a fly buzzing around a lamp. It is the shape of a vibration in the whole glass. That shape is called an orbital. The word makes it sound like a path. It is more like a weather pattern for a particle. The size of an electron ripple depends on how much energy it has. A very fast electron has a very tight, small ripple. It acts almost like a point. A very slow, cold electron has a big, soft ripple, sometimes the width of an entire molecule. This was confirmed in the 1920s, then confirmed again and again in every decade since. The ripple can do things no ball could ever do. It can bend around corners. It can pass through a barrier that, by any ball logic, it should not have the energy to cross. This effect is called tunneling, and it happens because a wave is a fuzzy thing that leaks slightly past walls it cannot fully climb over. Inside the Sun, hydrogen nuclei use tunneling every second to fuse and release light. Without ripples, stars would never shine. Take that in for a moment. The warmth on your skin in sunlight is proof that the inside of the Sun is ruled by spreading waves, not tiny balls. Scientists have even managed to steer these ripples. A team at a national laboratory in Germany used carefully tuned pulses of laser light to push and pull a single electron ripple around a small region, watching it stretch, split, and rejoin like a water droplet on a dancing speaker. The experiment was confirmed and repeated, and it still unsettles people who see the video. There is no ball anywhere in the footage, only shape moving. The electron by itself is already stranger than any object we have ever held, yet it is only one ripple on one field in a universe full of them. A quiet suspicion now begins to form. If every electron is a ripple on the same invisible ocean, then all of them might be closer to each other than anyone ever guessed. 1940, Princeton, New Jersey. A young physicist named Richard Feynman was working late at night when the phone rang. The voice on the other end belonged to his thesis advisor, John Wheeler. Wheeler was brilliant, a little strange, and famous for throwing out ideas so wild that half of them turned out to be right. Wheeler had one that night. He said, "Feynman, I know why all electrons have the same mass, why all electrons have the same charge, why every electron ever measured looks identical to every other electron ever measured. It is because they are all the same electron." Feynman listened. Wheeler kept going. "Imagine," he said, "one single electron zigzagging back and forth through time, travelling forward, then bouncing back, then forward again. Every time it crosses the present moment, we see a new copy of it, in a new place. Billions of them, trillions of them, all the electrons in every atom, in every star, in every galaxy, are one traveller, seen at different points of its own endless journey. The idea is called the one-electron universe. Feynman later admitted he did not fully believe it, but he never forgot it. Because even if the single traveller story is a fantasy, the observation underneath it is undeniably true. Every electron is perfectly, exactly, eerily identical. Take two electrons from opposite sides of the observable universe, one from a star 13 billion light-years away, one from the tip of your fingernail. Measure their mass, measure their charge, measure how they spin. Every number will match to the last decimal place any instrument can reach. No two snowflakes are identical, no two grains of sand are identical, but every electron everywhere is a perfect copy. Quantum field theory finally gave this strangeness a calm explanation. They are identical because they are ripples on the same field. Imagine one vast ocean stretching across the entire universe, and every wave on that ocean is made of the same water. Of course they are identical. They are the same stuff, moving in the same way. The ocean is the electron field. The waves are the electrons. When a new electron appears in a distant galaxy, the ocean here, in your coffee, trembles very slightly with it, because the ocean is one connected thing. Something follows from that picture, and it is almost too large to feel in one breath. Every electron in your body, every one of the 100 trillion inside your cells, is a ripple on the same ocean that is rippling right now, inside a star in another galaxy. The water between you and that star is the electron field. You're not separated from that star by empty space. You're connected by a silent, invisible medium that both of you are standing in. A physicist once said, during a talk, that this is the closest science has ever come to the old word fabric. The universe is a fabric. We are stitches in it. The same is true for photons and for quarks and for every other kind of particle. Each has its own ocean. Each ocean fills everything. If one of those oceans has been hiding the rule of why anything has weight at all, then finding it would not only be a discovery, it would rewrite what it means to be heavy and what it means to be light. Cambridge, England, 1928. Paul Dirac was a shy young physicist who barely spoke, even to his closest colleagues. He ate dinner in silence. He answered questions with single syllables. Inside his head, though, there was a storm going on. He was trying to solve one problem, make an equation for the electron that agrees with two things at once: quantum mechanics, which describes the very small, and Einstein's relativity, which describes motion at very high speed. Every attempt by every physicist so far had failed. The two theories refused to fit together. Dirac worked alone. He stared at the mathematics for months. Then, quietly, he wrote down a new equation. It fit. Both theories agreed. The electron behaved perfectly. There was a catch. His equation had two solutions. One described the electron. The other described something identical to the electron with the same mass, but with the opposite electric charge, a plus instead of a minus, a mirror twin. At first, Dirac assumed it was a mathematical ghost, a side effect of the algebra with no real meaning. He even tried to reinterpret it as the proton, because the proton was the only positively charged particle anyone knew about at the time. It did not work. The mirror twin had to weigh the same as the electron, and the proton weighs almost 2,000 times more. So, very carefully, Dirac wrote a new prediction. There must be a particle out there in the universe that looks exactly like the electron, but carries a positive charge. He called it, at first, an anti-electron. 4 years later, a young American physicist named Carl Anderson pointed a detector at cosmic rays coming from the sky above Pasadena, California. In his photographs, he saw a particle curving the wrong way in a magnetic field. The same mass as an electron, the opposite charge. The mirror twin falling out of space caught on film. Today we call it the positron. Then came the part that made every textbook shiver. When a positron meets an electron, both of them disappear, and two flashes of pure light fly out in opposite directions. Matter meets its mirror, and both become energy. Any hospital with a certain kind of cancer scan uses this effect every single day. A tiny amount of a chemical that gives off positrons is injected into a patient. The positrons collide with ordinary electrons inside the body. The flashes of light that come out are tracked by a ring of detectors, and a picture of the inside of the patient forms, one pair of flashes at a time. The lesson behind this miracle is deeper than the machines. Dirac's equation was telling the world that every particle we know has a mirror partner waiting, that every field, if you look closely enough, is double-sided. Positive and negative, matter and antimatter. Both sides are real. Both sides are already here. The universe, seemingly, was born with equal amounts of both. Something, in the first fractions of a second, tipped the balance. Matter won. Antimatter lost. Almost all of the antimatter vanished in a blaze of light, and the tiny leftover of matter became the stars, the planets, the atoms in your blood. A tiny imbalance. A trillionth of a tilt. Without it, nothing would exist, and the oceans that allowed that imbalance to happen are still here, still trembling, even in what we used to call the void. For most of human history, the word vacuum meant one thing: nothing, empty space, the absence of everything. Pump the air out of a jar and what is left is a little piece of nothing. Physics used to agree. Then, slowly it stopped. Imagine a sealed chamber in a laboratory. Inside, no gas, no dust, no light. The walls are chilled close to absolute cold, the lowest temperature the universe will allow. Every source of energy is removed. By the old definition, there should be nothing left to measure. Point a sensitive enough instrument inside and you find something anyway. A faint trembling. A constant shiver of electric and magnetic activity. Tiny flickers of energy appearing out of nowhere and disappearing again. Too fast for any clock to catch in full. They are there. They are always there. And they are what modern physics means when it uses the word vacuum. The reason comes from a rule called the uncertainty principle, written down by a German physicist named Werner Heisenberg when he was 24 years old. The rule is short. Nature refuses to let certain pairs of things both be exactly zero at the same time. Energy and time are one such pair. You cannot have absolutely zero energy for any meaningful length of time. The universe will not permit it. So the fields that fill space are forced to twitch. If they tried to hold perfectly still, they would be breaking the rule. Instead, they constantly borrow tiny amounts of energy from a kind of cosmic bank, make a small ripple, and pay the energy back before anyone can check. Those ripples are called virtual particles. A pair of them appears, an electron and a positron, or a quark and an antiquark, or a flash of virtual light. They exist for a flicker, they collide, they cancel, the bank is repaid. The vacuum looks empty again. This is happening in every cubic inch of space, right now. Inside your lungs, inside the glass of water on your table, in the stretch of sky between here and the moon. Billions of tiny transactions per second, in every spot, everywhere. A team of physicists in Germany made this real in a clever way. They set up a device that could look into a tiny region of vacuum for less than a quadrillionth of a second. In those brief windows, the instrument caught the faint electric shivers directly. The numbers matched the prediction of quantum field theory to a stunning degree of precision. Years of work on other experiments have added to the same picture. The shivering is real. Here is the uncomfortable thought behind it. If the vacuum is always twitching, then space itself is carrying energy, a small amount per cubic inch. Multiply it by the size of the observable universe, though, and the number becomes huge, almost unimaginable. Some estimates say the energy hiding in the pure vacuum of the cosmos outweighs all the stars and galaxies combined. So far, nobody has figured out how to tap into it. The fields refund the bank too quickly. Every attempt to pull energy out of nothing has failed. The shivering just hums, indifferent, yet its existence changes what emptiness means. A sealed, frozen, lightless chamber is not a pocket of silence. It is a quiet corner of a much larger restlessness. If that restlessness can reach out with real force, then it is only a matter of finding two objects small enough and close enough to feel it push. 1948, in a research lab in the Netherlands. A Dutch physicist named Hendrik Casimir was working on a strange little puzzle about why some very fine powders tended to clump together, even when there was no visible reason for it. During coffee one afternoon, he was talking with a colleague, and the conversation drifted toward the vacuum, the twitching vacuum, the one that never really sits still. Casimir went back to his office with an idea. He asked a simple question. What if you took two flat metal plates polished to a mirror finish and held them very close to each other inside a perfect vacuum, not touching, just close? Close enough that only a very thin gap of nothing separated them. Because the vacuum is constantly shivering with virtual waves, those waves would still be present between the plates and outside of them. Outside, space stretches away in every direction, so any kind of wave can fit. Between the plates, though, only certain wavelengths survive. A wave has to fit neatly into that narrow gap, the way a violin string can only hum at certain notes depending on its length. Longer waves get locked out. They simply do not fit. The result is a small imbalance. Outside the plates, a full choir of waves pushes inward. Inside the plates, only a smaller choir pushes back. The outside choir is louder. The plates get squeezed together by the uneven roar of nothing. Casimir calculated the force. It is tiny. For plates about the size of a postage stamp, held 1/100,000th of an inch apart, the pull is only a fraction of an ounce. For a while, it was an idea on paper, too delicate to test. 50 years later, teams at universities in Washington State and in California finally measured the force directly. They built instruments where one surface was a curved lens, the other a flat disc, both coated in gold. The experiments had to cancel out air, temperature, stray electric charges, even the gravitational pull of people walking by in the hallway outside. After months of careful work, the measurement came in. The plates were pulling together. The force matched Casimir's original calculation to within a few percent. Since then, the effect has been confirmed with metals, with semiconductors, with specially shaped surfaces, and even measured at nanometer distances inside tiny devices. It has been filmed indirectly, using lasers bouncing off the moving surface. Every check has agreed with the prediction. Something has to be doing the pushing, that something has no temperature, no light, no visible particles. It is the trembling of the fields themselves, the shivering of the vacuum, making itself felt as a gentle, stubborn pressure. The Casimir effect has a practical side too. In microchips being designed for future quantum computers, components are getting so small that the vacuum between them actually pulls them together and can stick parts that were meant to stay separate. Engineers are now forced to account for a force that, to the naked eye, is literally made of nothing. There is a philosophical weight to it as well. Every day, without fanfare, a physics lab somewhere measures the push of pure emptiness. Every day, the vacuum sends its answer. It is not quiet. It is not still. And it has something inside it that is old, patient, and present long before any of us were here. To understand just how strange that presence is, we have to look at what the fields do when everything is taken away from them, even the warmth. Temperature in ordinary life is a measure of how much the tiny pieces of a thing are jiggling. A hot cup of coffee has water molecules bouncing around quickly. A cold glass of water has them moving slowly. Cool it more and they slow down. Keep cooling and they slow down further. The deepest cold the universe allows has a name: absolute zero. Physicists write it as about -460 degrees Fahrenheit. At that point, classical physics says everything should stop. No jiggle, no movement, pure frozen silence. Reality refuses. Laboratories on Earth have chilled small clouds of atoms to within a few billionths of a degree of absolute zero. These are the coldest spots ever created. Colder than deep space, which still glows faintly with leftover heat from the birth of the cosmos. Colder than anything astronomers have ever measured anywhere. Colder than the shadowed craters on the far side of the moon. Even there, the atoms are still moving, a tiny jitter, a residual hum. The atoms cannot by law become truly still. The reason is the same uncertainty principle that keeps the vacuum twitching. Nature will not allow any system to have exactly zero energy. There's always a small leftover amount. Physicists call it zero-point energy. It is the lowest setting nature will let an object drop to, and the setting is not off. It is low, but it is on. Zero-point energy is not limited to atoms. It belongs to every field, everywhere. The electron field has a resting hum. The photon field has a resting hum. The Higgs field has a resting hum. Each one sits at its lowest possible vibration, and that vibration is still vibration. An experiment at the University of California once showed this in a dramatic way. A small metal paddle, about the width of a human hair, was cooled to almost absolute zero inside a sealed chamber. Using a careful laser system, scientists watched it for tiny movements. The paddle was shaking, a faint measurable wobble, perfectly matching the prediction for zero-point motion. Nothing was pushing it. The universe itself was refusing to let it rest. For most daily life, zero-point energy is far too small to notice. Your phone, your coffee mug, your body, all are jiggling at their own zero-point level, but the jiggle is drowned out by ordinary heat. Take the heat away, as physicists do in their coldest traps, and the jiggle is all that remains. Here is a thought that keeps some theoretical physicists awake. If every field across the cosmos has a lowest level hum, and the cosmos is unimaginably large, then the total leftover energy of space should be huge. Calculations have been tried. The number that comes out is famously, embarrassingly, catastrophically wrong by about 120 orders of magnitude. It is the worst mismatch between theory and observation in the history of physics. Nobody knows why the real vacuum carries so much less energy than the math predicts. It is one of the deepest unsolved mysteries in the field. Some physicists suspect a hidden rule is cancelling out almost all of it. Others suspect the math itself is incomplete. The hum is there. The puzzle is why it is so quiet. Somewhere inside that hum, tiny particles flicker into view and vanish again, short-lived ghosts that obey rules of their own. Picture a pool of dark water at midnight. Every so often, a single bubble rises from the bottom, breaks the surface, and pops. Gone before you can point at it. Another one rises somewhere else. Another. The surface of the water looks calm from a distance. Up close, it is speckled with tiny flashes of motion, each one over almost as soon as it begins. That is the closest everyday image for what physicists call virtual particles. Virtual particles are small, temporary ripples in the quantum fields. They appear in pairs. One particle and its mirror twin, its antiparticle. They exist for the shortest imaginable flash of time. Then they fall back into each other and disappear. The energy they borrowed is returned. No record remains, except in the effects they leave behind. How long do they last? For particles as light as an electron and a positron, the answer is something like a millionth of a billionth of a billionth of a second. A flicker so fast that no direct detector can catch it in the act. Many readers, hearing this, reasonably ask, if we cannot see them, how do we know they are real? The answer is that they leave fingerprints. Consider the electron itself. Place an electron in a magnetic field, and it should spin a certain way, predicted by simple physics. When scientists measure very carefully, though, the electron's spin is slightly off, a tiny correction. As if something invisible were bumping it as it turned. That something is the cloud of virtual particles that constantly surround every real electron. The electron is never truly alone. It is always wrapped in a humming swarm of briefly existing twins and photons, winking in and out, jostling it gently from every direction. When physicists include those invisible bumps in the calculation, the answer matches the measurement to more than 10 decimal places. No other theory in science fits reality that precisely. It is often called the most accurate prediction ever made. Those tiny bumps are also, in a real sense, what holds atoms together. When two electrons push away from each other because their charges repel, the repulsion is carried by virtual photons flickering between them. When the quarks inside a proton hold on to each other, they do it by exchanging virtual versions of the particles that carry the strong force. Forces, in the modern picture, are not invisible ropes. They are conversations made out of virtual particles. A laboratory in Illinois spent years measuring the behavior of a heavier cousin of the electron, called the muon, inside a special magnet ring. The muon's spin showed a tiny extra wobble, slightly different from what the standard theory predicted using only the known virtual particles. That mismatch, still being studied, is one of the hottest mysteries in modern physics. Some researchers think it hints at new, undiscovered particles flickering through the vacuum. Experiments continue. Virtual particles are a good reminder that in quantum field theory, exists is a soft word. There is a spectrum from eternal and stable down to whispers that last less than any clock can measure. What matters is whether the whispers change the outcome of things we can measure. They do, over and over. And someone long ago worked out how to draw these whispers on paper in a way so simple that even undergraduates could use it to predict the behavior of the universe. Cornell University, late 1940s. Richard Feynman was sitting at his desk surrounded by pages of long, ugly equations. Quantum field theory had just been invented, and even the people who invented it could barely use it. Every calculation took weeks. Every small correction unleashed an avalanche of symbols. Physicists were beginning to worry that their own theory might be too complicated for human minds to handle. Feynman stared at the mess. He had an idea that would make his name legendary. He started drawing pictures, a straight line for an electron, a wavy line for a photon, a point where lines meet marking an interaction. Read the picture from left to right, and it told a story. An electron comes in, emits a photon, continues on. Two electrons meet, exchange a photon, push apart. Each line and vertex corresponded exactly to a piece of the original math. Add up every possible picture for a given event, and you got the full answer. His colleagues at first thought he was playing. Then they tried his method. A calculation that used to take a month took a day. The drawings became known as Feynman diagrams. They are so useful that today almost every physics student learns them before learning the full equations they stand for. Even theorists working on brand new ideas still start by sketching little stick figures of electron lines, quark lines, and wavy photon lines before writing down a single number. A 15-year-old can learn in an afternoon to read a basic Feynman diagram. Without one, the calculations are nearly hopeless. There is something deeper going on than a mere convenience. Each diagram represents one possible path through the fields, one way the event could happen. In quantum field theory, nature does not pick a single path. It adds up all of them. An electron travelling across a room takes every possible route at the same time. It bounces off virtual particles. It loops. It meets itself. Every diagram you can draw for its journey, with all possible middle events, contributes a small amount to the final outcome. When all the possibilities are summed, the result is what you measure in the laboratory. This insight was first explored by Feynman for light and electrons, and later extended by others to every known kind of matter and force. Every particle interaction you have ever heard of, from a proton smashing another proton in a giant collider, to the gentle capture of a photon in the back of your eye, is the sum of countless tiny diagrams, each one a ripple pattern in a field. Feynman himself had a famous way of describing this. The universe, he said, works by trying every possibility and adding them up. The visible world is the after-image of a contest that took place in the fields. A group at a laboratory in Switzerland used this style of calculation to predict, ahead of time, how often a certain rare particle should appear in a collision. Years later, when the machine finally ran, the number matched to the second decimal place. Pictures, drawn on chalkboards, had predicted a real event in a tunnel 100 meters underground. Diagrams made the invisible feel sketchable. They also reveal something quiet. If every interaction is a sum over paths, then the simplest particle we know, the one that carries light, is itself a conversation in the field, waiting to happen. Hold up a hand under a desk lamp. Warmth settles on your skin. A soft glow reflects off your palm. It feels like a steady stream is arriving from above. Zoom in, slow the picture down. That steady stream is not steady at all. It is made of tiny pulses, each one a packet of light, flying from the bulb to your hand. The pulses are called photons. A single bulb, in a single second, can throw trillions and trillions of them out in every direction. Each photon is a ripple in a field that covers the entire universe. The photon field. Other names for it exist, but the short one works. It is present in your room, in the heart of the sun, in the emptiest stretch of intergalactic space. Whenever something with an electric charge wiggles, the photon field ripples in response, and that ripple moves outward at the fastest speed anything can move, the speed of light. Here is the first surprise. The photon has no weight, not a tiny weight, none at all. Every careful experiment ever done has come back with the same answer. A photon is a ripple that carries energy without carrying any mass. That is why it can travel at the maximum cosmic speed. Anything with weight would need infinite push to reach that speed. A photon, being weightless, simply is that speed, always. The second surprise, a single photon from a laser can be split in a special crystal into two fainter photons, both with exactly half the energy of the original. Those two together behave as if they are a single pattern stretched across space. Send one to a detector on the left, the other to a detector on the right, and measure their properties. They match every time in a way that no pair of ordinary objects could. This effect is called entanglement, and it has been confirmed in laboratories on every continent. The record for distance between two entangled photons at the time of writing is over 800 miles, measured using a Chinese satellite in orbit that beamed the pair to two ground stations far apart on the surface of the planet below. The third surprise is what happens when one photon hits your eye. A single photon, if it carries just the right amount of energy, can kick an electron inside a cell at the back of your retina. That kick starts a chemical chain reaction that sends a signal down your optic nerve. Your brain reads that signal as a flicker of light. Human eyes, under the right conditions, can actually detect a single photon at a time. A laboratory in New York ran the experiment with volunteers in complete darkness, firing single photons at their eyes and asking them to press a button when they saw something. The volunteers performed slightly better than random guessing, even at the single photon level. A ripple on a field landing on a single cell, and a human being noticing. Every colour you see is a photon of a certain frequency. Red is slow ripples, blue is fast ripples. Beyond blue, where ripples become too fast for your eyes to register, sit ultraviolet, X-rays and gamma rays, all the same kind of wave, all still photons, just tighter. Light is one simple thing, a vibration in 1C. Every colour, every warmth, every signal across space. If a single wave can take every possible path and still arrive on time, the picture of how that is possible is one of the gentlest strange things in all of physics. A lifeguard on a beach spots a swimmer in trouble out in the water. She has to reach the swimmer as fast as possible. She can run quickly on sand and swim more slowly through water. The fastest path to the swimmer is not a straight line. It bends slightly at the shore. She runs a longer distance on land to shorten the slower distance in water, and her total time to reach the swimmer is the smallest it can be. Light does the same thing. When a ray of sunlight moves from air into a glass of water, it bends. The bend is the same kind of shortcut the lifeguard takes. Light travels fast through air and slower through water, and the angle it chooses always turns out to give the quickest possible trip from the sky to the bottom of the glass. A French mathematician named Pierre de Fermat noticed this in the 1600s and called it the principle of least time. For 2 centuries it was a curious rule with no explanation. Light seemed to pick the quickest route as if it knew the destination in advance. In the 20th century, quantum field theory answered the puzzle, and the answer is stranger than the question. Light does not choose a path, it tries every path at once. When a photon leaves the lamp above your desk, the photon field sends ripples in every possible direction. Straight lines, curved lines, crazy zigzags, paths that loop around the moon and come back. Every one of them contributes a tiny piece to the final wave. Most of those pieces, however, cancel each other out. The crazy paths arrive at slightly different times from each other. Their peaks line up with troughs from a different path, and together they add up to nothing. One set of paths does not cancel. The paths close to the quickest one. Those paths arrive almost at the same time as each other. Their peaks line up with peaks. Their ripples add together, loud and strong. So the photon appears to have travelled the fastest route, because that is the only route where the field's vibrations did not cancel themselves. The illusion of a chosen path is really a survival of the loudest sum. Richard Feynman showed this by calculation, and then, in his lectures, by slow, careful pictures. He drew small arrows for each path. He added them like tiny vectors. 99% of them pointed in scattered directions and cancelled. The ones near the fastest path all pointed the same way. They added up into a real signal. Students watching this for the first time often feel a little dizzy, because the lesson is that the straight-line path of a single photon is not a fact about the photon. It is a statistical leftover of trillions of invisible options, most of which vanished before reaching your eye. A team at a university in Canada tested this using a setup where they blocked certain paths and let others through in careful arrangements. The light patterns that emerged exactly matched what the sum over paths math predicted, including strange patterns that could not possibly be made by any single straight ray. Light does not pick. Light explores. Everything that ends up at your retina is the echo of a million silent possibilities that fell away. And while light plays that slow game of exploration, another field, shorter in range and louder in its pull, is holding every atom in your body together with invisible ropes of color. Inside every atom of every object around you is a tiny, densely packed center called the nucleus. Inside the nucleus are protons and neutrons. Inside each proton and neutron are three even smaller things called quarks, bound together by a force so strong that it has no everyday analogy. That force is called, plainly, the strong force. It is the loudest fundamental force in the universe, and also the shortest in reach. At the scale of a single proton, across a span smaller than a trillionth of an inch, it is hundreds of times stronger than the electric force that tries to push same-charged particles apart. Outside the proton, a tiny distance away, it fades to almost nothing. Within its range, it is the king. Beyond, it is silent. A new field explains it. Physicists gave this field an unusual name. They called it the color field, even though it has nothing to do with the colors in light. Here is the idea. Every quark carries a kind of charge, but not the usual electric charge. This new charge comes in three varieties, labeled for convenience as red, green, and blue. A normal proton has one quark of each, one red, one green, one blue. When you add the three labels together, they cancel out, like the three colors of light mixing to make white. From the outside, the proton looks neutral. Inside, it is a three-cornered battle held together by the color field. The force is carried by its own particles, not photons this time, something called gluons. They zip between quarks constantly, changing the colors of the quarks as they go. A red quark, after a gluon flies to it, might become a blue quark. The balance of the three colors, however, always stays perfect. White on the outside. Gluons themselves are strange. Photons carry no electric charge. Gluons, in contrast, carry color charge. They interact with each other. Two gluons passing each other can deflect and spin around. It is as if the ropes holding an atom together were also pulling on each other. This creates an effect called confinement, and it is where the strong force becomes unlike anything from ordinary life. Try to pull two quarks apart. As you pull, the color field between them does not get weaker. It gets stronger, like a stretching spring that refuses to break. Keep pulling, and eventually, there is so much energy stored in the field that it turns into a brand new quark and antiquark right in the middle. Instead of separating, the stretched rope snaps by creating two new quarks. You now have two pairs of quarks where you had one. No free isolated quark ever escapes. Every quark in the universe today is trapped inside a proton, a neutron, or one of their heavier cousins. A free quark has never been seen, anywhere, by any experiment. Every nucleus in every atom in every planet and every star is a little prison, and the bars are woven from the color field. Laboratories in Illinois, New York, and Switzerland have verified this with decades of collisions. When high-speed beams smash protons together, the fragments always come out as new proton-like particles, never as bare quarks. The color field is the loud, short-range grip that keeps every piece of ordinary matter from flying apart. Without it, there are no atoms, no molecules, no planets, no us. Inside that grip, the lives of quarks are even stranger than the rule that traps them. Imagine two small magnets attached to the ends of a soft rubber band. The magnets pull away from each other. The rubber band stretches, and after some force it snaps. Now swap the rubber band for something new, a band that, when you pull it, gets stronger the more you stretch it. The harder you pull, the more it resists. That is, roughly, how the color field acts between two quarks inside a proton. The color field between a pair of quarks pulls itself into a narrow tube, almost like a taut string. Physicists sometimes call it a flux tube. Inside that tube, the field is intense. Energy is stored along its entire length. As the quarks move apart, the tube stretches and the energy inside it rises. Not in a decaying way, the way gravity weakens with distance, in a steady, unbroken climb. This creates the strange rule of confinement. A quark can dance around freely inside the tube. It can wiggle. It can oscillate. It cannot step outside. Every attempt to pull it away only pours more energy into the stretching string. At some point, the string has absorbed so much energy that nature finds a cheaper option. Instead of stretching further, the string uses the stored energy to create a brand new quark and antiquark out of the vacuum. The original string breaks in the middle, and both ends of the break immediately grow new caps, one new quark on each side. You now have two shorter strings, each with a fresh pair of quarks, instead of one long stretched string. Scientists have watched this happen indirectly. In the Giant Collider near Geneva, beams of protons smash together at nearly the speed of light. When a quark inside one proton is kicked hard, it tries to fly out. Before it can get anywhere, the colour string snaps, creating a shower of new particles, almost all of which bundle themselves into little packets, each containing 3 quarks or a quark-antiquark pair. These sprays are called jets. The detector records them as bursts of dozens or hundreds of particles, all flying in roughly the same direction. Not a single lonely quark has ever been recorded anywhere. Millions of collisions, billions of collisions. Every time the quarks dress themselves in buddies before they reach the detector. The rule of confinement has never broken, not even once. This is how every proton and neutron in your body stays intact. 3 quarks in each proton, 3 in each neutron, each trio permanently bound by the colour field, each trio walled off from ever being alone. There is more going on inside a proton than those 3 quarks, though. The colour field itself, constantly snapping and recreating pairs, fills the inside of a proton with a fizzing sea of virtual quarks and gluons. If you weigh the 3 permanent quarks and add their masses together, they account for only about 1% of the proton's total weight. The other 99% comes from the energy locked in the colour field surging inside it. Stop there for a second. 99% of the weight of every object you have ever touched, every chair, every drop of water, every cell in your own hands, comes from the energy of the colour field, vibrating inside the protons of its atoms. The matter you feel is mostly stored motion, tied into a standing pattern by invisible strings. A field much quieter and much slower than this one has been busy for over 4 billion years, calmly keeping a different fire alive. Step outside on a clear morning. Feel the sunlight on your face. That warmth has been travelling for about 8 minutes to reach you. It was born in the core of the sun, from a reaction that depends on one of the strangest fields in physics, the weak field. It has a plain name for a reason. Its force is, well, weak. Not weak like gravity. Weak in the sense of short-lived and selective. It acts across distances 1,000th the size of a proton, which is itself already microscopic. Outside that tiny range, it does almost nothing. Inside, it does something special. It changes the identity of particles. This is the one force in the universe that can turn one kind of particle into another. Here is the simplest case. An ordinary neutron, left by itself outside a nucleus, will live on average about 15 minutes. After that it breaks down. It turns into a proton, an electron, and a tiny ghost called a neutrino. The neutron is gone. 3 new things have taken its place. That change is the weak field at work. One of the quarks inside the neutron quietly flipped its type, and when that flip happens, an electron and a neutrino come out to balance the books. Without that flip, the sun could not shine. Inside the sun, protons fuse together to build heavier atoms, eventually helium. The very first step of that chain requires a proton to turn into a neutron. Two free protons cannot simply bond. One of them must quietly change flavor, using the weak field, so the pair can hold together. The weakness of this force is exactly what makes it rare, which is exactly why the sun burns slowly and steadily for billions of years, instead of flaring up and burning itself out in a single huge day. A star where the weak force was even a little stronger would have detonated long before any planet could form. The weak field is also carried by its own particles much heavier than photons. They're called the W and Z bosons. Photons have no weight. W and Z particles are each close to 100 times the weight of a proton. Their heaviness is exactly why the force is short-ranged. A heavy messenger cannot travel far. It blinks in, does its little trick, and is gone. Scientists first caught these heavy messengers directly in the 1980s in an experiment at a European laboratory in Geneva, where a team led by Carlo Rubbia smashed protons and antiprotons together. In the debris, the signature of the W and Z particles appeared exactly where theory said they should. Rubbia and his colleagues got the news at around 3 a.m. He called his partner half asleep and said, "We found them." The discovery won him a Nobel Prize the following year. The weak field has another quirky property. It plays favourites with left and right. Inside its interactions, the universe treats mirror images differently. A mirror-flipped version of a weak event does not look the same as the original. Every other force in physics is perfectly symmetric in a mirror. The weak field, alone, is not. For reasons nobody fully understands, nature has a handedness, and the weak field is the one place you can see it. A force shy, strange, and hand-picky keeps every star burning, and hiding one layer deeper, an older field gave everything else the weight it carries. For most of the last century, physicists had a problem they could not hide. Their best theory of particles worked beautifully, except for one embarrassing leak. If the equations were taken at face value, every known particle should weigh exactly 0. Electrons, quarks, the heavy messengers of the weak field, all of them weightless. Perfect ripples flying at the speed of light. That is plainly not how the world is. An electron has a tiny but real weight. A proton has a bigger one. The heavy messengers of the weak field are huge. Reality clearly handed out weight. The theory could not explain how. In the 1960s, a handful of physicists working separately in Scotland, in the United States and in Belgium, proposed a fix. The most famous of them was a quiet Englishman named Peter Higgs. The idea was unusual, even by quantum field standards. They said, imagine that the entire universe is filled with an extra field, invisible, present in every cubic inch of space, in every direction. This new field is sluggish and thick. It lies flat and steady at a constant value, everywhere. When a particle moves through it, the field drags on the particle in a specific way, depending on how strongly that particle talks to the field. The dragging gives the particle a resistance to acceleration. That resistance is what we experience as weight. A simple picture helps. Imagine walking through a large room full of honey up to your knees. Your legs move slowly. The honey drags on you. You feel heavy. Now imagine a different person, walking through a room full of water. The drag is less. They feel lighter. Someone running through a room full of air feels almost no drag at all. That is roughly how the Higgs field treats different particles. A photon does not interact with the Higgs field. It slips past as if the honey were not there, weightless, free to race at the maximum cosmic speed. A top quark, on the other hand, interacts with the Higgs field very strongly. It wades through the honey on its belly, heavy, slow to change direction. An electron feels only a little drag. A muon, a heavier cousin of the electron, feels a little more. The pattern of weights across all the known particles is a pattern of how strongly each one talks to that one omnipresent field. Here is the strange part. Every particle, everywhere, is always inside the Higgs field. There is no corner of space where the field is missing. You, reading this in your mind, are sitting inside it. Every electron in your body, every quark in every proton is dragging through it right now. The weight you feel standing up is, in the end, the sum of trillions of tiny ripples being held back by the same invisible sea. This was only an idea for almost 50 years. Chalkboards were covered in it. Papers were published about it. Nobody had directly detected the field itself. Without a direct sighting, nobody knew for sure it was there. What would prove the field existed? Simple to say, very hard to do. Punch it hard enough to make it ripple. A ripple in the Higgs field would be a new particle, the Higgs boson, and catching it would require a machine bigger than any ever built. Underneath the border between France and Switzerland, deep beneath farm fields and small villages, that machine was already under construction. Return to the honey-filled room for a moment. Some people sank knee-deep and could barely move. Others walked like the honey was not there. That uneven treatment is the core mystery of the Higgs field, and it leads to one of the deepest questions in physics. Why do different particles feel different amounts of drag? The short answer is built into the math. Each particle has a number attached to it called its coupling to the Higgs field. A big number means a strong tug. A small number means a gentle tug. 0 means no tug at all. The long answer is that nobody truly knows where those numbers come from. Photons have a coupling of 0. They do not notice the Higgs field in any way. A ripple in the photon field moves through a region packed with Higgs field, and it glides on without losing a drop of speed. That is why light always travels at the absolute top speed the universe allows. The Higgs honey is, for light, invisible. An electron has a small coupling, a tiny tug. As an electron ripple moves through space, the Higgs field pulls on it gently, the way a thin mist slows a runner. The electron feels a little drag, and that drag shows up as a little weight. A top quark, the heaviest particle ever discovered, has a huge coupling. The Higgs field grabs it hard. Every step is heavy. A top quark weighs about 300,000 times more than an electron. Nothing else in the particle world is close. Here is the unsettling detail. Each particle's coupling looks hand-picked. There is no formula in the standard theory that predicts it from first principles. The numbers are simply measured in experiments, written down, and plugged in. Why the top quark was given such a strong grip on the Higgs field and the electron such a weak one is a matter of silent chance as far as current physics can tell. It is one of the biggest open questions in the field. Some theorists suspect there is a hidden pattern, an undiscovered deeper rule. Others suspect the numbers are what they are because, in a multiverse of possibilities, we happen to live in the universe where life could form around them. A practical consequence of these couplings is stability. The electron and the up and down quarks, the light members of the family, have small couplings. They are the building blocks of every ordinary atom. The heavier particles with larger couplings are unstable. They form briefly in high-energy collisions and decay within fractions of a second. The universe around us is mostly made of the light, low-drag particles. Mass and stability are two sides of the same Higgs coin. Picture a crowd in a hallway. A few celebrities are among them. Everyone pauses to talk to a celebrity for a moment as they move past. Ordinary people, the ones nobody recognizes, pass through the crowd unnoticed. The celebrities travel slowly through the same hallway because they are constantly surrounded by delays. The hallway is the Higgs field. The crowd is the field itself, responding to each type of particle. Some particles are celebrities in the room, some pass unrecognized. This picture was only theory until the year 2012. That year, a ripple in the Higgs field appeared on a graph in Switzerland, and the entire physics world stood up from its desks to see it. Deep under the fields of Switzerland and France, in a ring-shaped tunnel about 17 miles around, sits the largest and most expensive scientific machine ever built. Physicists call it a particle collider. Inside, two beams of protons are whipped up to nearly the speed of light, travelling in opposite directions. At 4 points along the ring, the beams are crossed, and the protons crash into each other. Each collision is a burst of energy, concentrated in a space smaller than a single atom. Out of that burst, for a fraction of a second, the fields around the collision spot shiver. New particles pop out of the shivering, fly outward, and pass through giant detectors the size of cathedrals. Every flash, every track, every tiny deposit of energy is recorded. Physicists around the world had been chasing one particular tremor for almost half a century. A ripple in the Higgs field. If the field was real, then hitting it hard enough should make a wave in it, and that wave would be a brand new, short-lived particle. Heavy, unstable, gone almost the moment it appeared. The Higgs boson. The machine had to be big because the Higgs boson is heavy. Around 125 times the weight of a proton. Making one requires more energy than any machine before it had ever delivered. On the 4th of July in the year 2012, two large experiments inside the tunnel run by separate teams called a press conference in a packed auditorium in Geneva. The teams had kept their results hidden from each other until the very last moment to avoid bias. On stage, one by one, they showed their graphs. Both teams had the same bump. At exactly the energy where the Higgs boson should appear, their data showed a small, stubborn peak above the background noise. The peak was in the right place, with the right shape, at the right strength, in both experiments at the same time. The odds of such a thing happening by accident were vanishingly small. The auditorium erupted. Peter Higgs, 83 years old at the time, was sitting quietly in the audience. When his theory was finally shown to be right, he was seen wiping his eyes. A reporter asked him how it felt. He answered softly that he never thought in his lifetime that he would see it. The following year, he and his colleague François Englert were awarded the Nobel Prize for that work. Since that first sighting, the Higgs boson has been made many more times. Its properties have been measured in fine detail. Its weight, its lifetime, the ways it decays into other particles. Every measurement has so far matched the original prediction. The field, the drag, the mass, all of it, is behaving exactly as the math forecast. There is still mystery left. Some measurements hint faintly at small deviations from perfect agreement. Physicists are watching closely. A real deviation would be a sign of new physics, hiding behind the Higgs, pointing at something unknown. One discovery settled so far. The Higgs field is real, and it has been pooled across the entire universe since the first microseconds of time. It gives everything with weight its weight. Underneath this quiet drag, however, an even deeper question waits. Why does the Higgs field sit at the value it sits at? Why did the universe long ago fall out of a perfectly symmetric state and land in this particular one? The word symmetry has a strict meaning in physics. A system is symmetric if it looks the same after you change it in some way. A perfect sphere is symmetric because it looks the same no matter how you rotate it. A snowflake is symmetric in 6 directions. A square is symmetric in 4. Physicists love symmetry because it simplifies equations. The more ways a system looks the same, the fewer numbers you need to describe it. For most of the last century, the deepest theories of physics have been guided by the search for beautiful symmetries. Here is the twist. The universe we live in is not symmetric at all. It is a lopsided, uneven, detailed mess. There is matter and almost no antimatter. There are 3 spatial directions and 1 time direction. There are 4 different fundamental forces, each with its own personality. Different particles have different weights. There are left-handed rules in the weak field that do not match their right-handed mirror images. None of this is symmetric, so physicists faced a puzzle. If the deep math loves symmetry, why does the visible world look so broken? The answer is called symmetry breaking. The idea is that the universe started out highly symmetric, in its earliest fractions of a second. All the forces were unified. All particles had similar properties. Fields sat in perfectly balanced arrangements, indifferent to direction. Then, as the young universe cooled, something tipped. The system fell out of its balanced state into a lower energy one, like a ball rolling off a peak and coming to rest in a crooked valley. Once it landed, the old symmetry was hidden, even though the underlying rules still had it written in. A simple image. Picture a thin pencil balanced, point down, on a flat table. Before it falls, it is perfectly symmetric. It looks the same from every angle. It could tip in any direction. Once it falls, it points one way. The symmetry of the starting position is gone. The underlying system, a pencil on a table, still has no preferred direction. The pencil does. The world the pencil landed in has an obvious asymmetry. That is what physicists believe happened to the early universe, only in field form. The Higgs field, in particular, started out at an unstable symmetric value in the earliest cosmos. As the universe cooled, the field slid down into a lower, slightly off-center resting value, the one it still sits at today. By landing there, it froze in a specific pattern, and that pattern is what gives each particle its current mass and behavior. Before the fall, photons, W and Z bosons and other messengers were all interchangeable. After the fall, photons became weightless and travel at the top speed, while W and Z bosons became heavy and short-ranged. A team of theoretical physicists in the 1970s worked out the details of this. It turned out to match the numbers from the colliders when machines caught up decades later. The mathematics of broken symmetry predicted the weights of the W and Z bosons before anyone had seen them, and the prediction agreed with the measurements to within a percent. The lesson behind this is quietly philosophical. A perfectly symmetric universe is boring. No distinctions, no forces with different personalities, no particles with different weights, no chemistry, no life. A perfect symmetry would be death. The universe became interesting by falling out of its balance. Everything we are is a consequence of that fall. A gentle image is about to show how deep that gentle fall really goes, using a tool no more complex than a pencil and a table. Take a pencil, a real one, and try to balance it on its sharpened point on a flat table. Hold the eraser end with one finger, let go and watch. The pencil teeters for a brief moment, then falls. It always falls. It never stays upright for long, no matter how careful you are. Here is the interesting part. Before it falls, every direction around the pencil is the same. Up on the table there is no north and no south, no preferred side for the fall. The pencil could tip any way. It is a perfectly symmetric situation. Every angle has equal odds. After the fall, the pencil points in one specific direction. The other direction's lost. The world with a fallen pencil has an obvious arrow in it, and there is nothing deep about why that particular arrow was chosen. A tiny draft, a microscopic vibration of the table, any small random push decided the matter. This is called spontaneous symmetry breaking, and it is one of the key ideas in modern physics. The full symmetry of the situation is still there in the setup. The table is flat. The pencil is perfect. Gravity pulls equally in every direction on the pencil tip. The symmetry is in the rules. The broken symmetry is in the result. The early universe did something very similar. Deep in the first fractions of a second after the cosmos was born, the Higgs field was humming, high and unstable, at a perfectly symmetric value. In that moment there was no difference between different kinds of messenger particles. Everything treated the Higgs in the same way, because the Higgs field itself had no preferred setting. The universe was extremely hot, and the field had plenty of energy to stay up high, balanced on its tip, like the pencil before it fell. Then the universe cooled, rapidly, enormously. Within a timescale far shorter than any blink, the Higgs field tipped. It fell off its balanced peak and rolled down into a lower, calmer value. Like the pencil, it now pointed one way. Every particle in the universe was forced to respond to that one specific setting. From the outside, this looks like a universe that simply has a certain Higgs value and certain particle masses. From the inside of the theory, it is a fallen state. If the universe had tipped slightly differently, the particle masses might have come out differently. Electrons could have been heavier, quarks lighter, photons dragged. Chemistry would have been different. Atoms might not have formed. Life would be impossible. Physicists have asked calmly what would happen if the Higgs field ever tipped again into a deeper valley, a cosmic pencil falling a little further. This idea is called vacuum decay. Calculations suggest that under very extreme conditions, there could be an even lower energy state that the Higgs field could, in principle, slide into. If it did, a bubble of the new deeper state would appear somewhere in the cosmos and expand outward at nearly the speed of light. Inside the bubble, the laws of chemistry would be rewritten. Every atom in its path would fall apart. The calculations show this is astronomically unlikely to happen in our lifetime. The odds are tiny. Current measurements show the Higgs field appears to be in a long-lived metastable state, expected to remain for times far longer than the current age of the universe. A small shiver, though, comes with the knowledge that the universe is balanced on a very quiet pencil, and even in stillness, the question of what comes next is never quite closed. Turn the imagination backward in time, past galaxies forming, past stars lighting up, past the first atoms, the first nuclei, the first simple particles, deeper, back when the universe was less than a trillionth of a second old and unimaginably hot. At that moment, almost all the fields in physics were behaving in a way that no longer exists anywhere in the present cosmos. In that first stretch of time, the photon field and the weak field were not separate. They were a single field. Physicists call it the electroweak field. When the cosmos was young and dense and furnace hot, the two forces we know today as electromagnetism and the weak force were two sides of the same deeper thing. The messengers that now carry light and the heavy messengers that now change particle identities were indistinguishable from each other. They all shared the same rules and the same behavior. Then the universe cooled. The Higgs field tipped into its lower valley, and the single electro-weak field split in two. From that split, 4 different messenger particles emerged. The photon, light and weightless, became free to sail across the cosmos forever. The W+, W-, and Z particles, the heavy messengers of the weak force, became trapped inside their short range by the new drag the Higgs field placed on them. What had been one team became 2, with very different personalities. This is the strongest piece of evidence physicists have that the forces of nature are unified at deeper levels and only appear separate to us because we live in a cold, fallen, late-stage universe. Experiments at several colliders confirmed this picture over the last few decades. By slamming particles together with enough energy, physicists can create conditions briefly similar to the very early universe. In those tiny fireballs, the electroweak split can be probed and mapped. The relationships between photons, W and Z bosons match what the unified theory predicts, with precisions reaching many decimal places. The unification suggests something almost poetic. Every time a magnet sticks to a refrigerator, every time sunlight reaches your face, you're watching half of a broken unity in action. The weak field sits right beside the photon field in every cubic inch of space, wearing a different coat than it used to, carrying a different weight than it used to, yet once they were the same thing. A natural next question arises. If 2 of the 4 fundamental forces were once a single force, could the other 2 also join in at an even earlier, even hotter moment? Theoretical work ongoing suggests that yes, maybe. The strong force might have merged with the electro-weak force at temperatures far beyond anything a particle collider has ever reached. That merger would take place above what physicists call the grand unification scale. Some theories predict that at that deeper level even quarks and electrons become different faces of the same underlying particle. Gravity is the stubborn holdout. Every attempt to pull it in has hit walls of mathematics. A fully unified description of all 4 forces remains the biggest unsolved project in theoretical physics. There is a lesson in the partial success so far. The universe we see, with all its categories and differences, might be a late-stage costume party. Underneath, there may be only one thing, dressed in many outfits because the room got cold. To test these ideas, physicists cannot go back in time. They have to do the next best thing, simulate the early cosmos inside a computer, step by step, across an imaginary grid. A quantum field theory is a beautiful thing on paper. Smooth equations, continuous fields that fill space at every point. When physicists try to calculate precise numbers from those equations, however, they hit a wall. The fields vary across an infinite number of points. The math becomes a mountain of infinities. Simple operations take forever. Even basic predictions in some cases turn out impossible to solve by hand. Somebody had to find a trick. The trick is called a lattice. Imagine replacing the smooth space around you with a fine 3-dimensional grid, like a regular pattern of tiny dots filling a room. Each dot is a location where the field has a value. The dots are connected to their neighbours by lines. Instead of treating the field as a smooth surface, physicists treat it as a swarm of numbers at the dots, changing over time. The smaller the grid spacing, the closer the simulation gets to the real continuous field. As computers grow more powerful, the lattice can be made finer. This approach turns a problem that was impossible to solve with equations into a problem that can be solved by huge computers grinding away on grids of numbers. For decades, large research centres around the world have run these simulations on some of the fastest machines ever built. At a national laboratory in Japan, at centres in the United States, at supercomputer clusters in Germany, rooms full of quietly humming servers run month-long simulations of a single proton. Numbers in the grids twist and update. A virtual colour field snaps and reforms. A virtual proton sits inside the computer, tested and probed. The results have been stunning. Lattice simulations have correctly predicted the weight of the proton from first principles, starting only with the rules of quarks and gluons. They have predicted the internal structure of neutrons and heavier particles, matching what experimental physicists measured in accelerators. They have begun to probe the very early universe, simulating what happened as the strong force came into its final shape during cooling. The lattice is a quiet kind of miracle. It shows that the fundamental rules of quantum field theory, when turned into numbers on a grid, reproduce the weights, sizes, and behaviours of real particles made of quarks. Nothing needs to be added by hand. No fudge factors. Just the math chopped into a grid, fed to a computer, and run. Lattice work has also revealed surprises. In some simulations, researchers watch the colour field form specific shapes around pairs of quarks. Long, narrow tubes. Exactly the kind of tubes that theoretical physicists had long suspected, based on indirect reasoning. The simulations gave the tubes a visible form on a graph. There are limits. Lattice calculations for the weak field, and in particular for processes involving time-dependent phenomena, are extremely difficult. Gravity on a lattice is unsolved. Some properties of the fields, like how they behave far from equilibrium, remain out of reach. Still, for the strong field, lattice simulations have been so successful that they are now used to test the predictions of the underlying theory itself. If a lattice simulation disagrees with an experiment, physicists take it as a hint that there might be a flaw in their understanding. So far, the simulations keep matching experiments, decimal after decimal. Inside those grids, every simulated particle is a vibration, a standing wave, sitting quietly at a lattice point, or rippling across many. That fact is more than a programming detail. It is the core truth about what a particle really is. Strike a bell. The sound you hear is not the bell itself. The metal was already there, silent and still. The sound came from the way it started vibrating after the strike. The bell was the medium. The tone was the excitation. In quantum field theory, a particle is exactly that kind of tone. A particle is an excitation of a field, a region where the field is vibrating at a certain frequency and pattern with a certain energy. The field, like the bell, is already present everywhere. The particle is the tone it is playing at a particular place and moment. Take the electron field again. Across every cubic inch of space, the field sits quietly at its lowest vibration, humming faintly. Somewhere, a collision dumps energy into a small region. The field lifts up into a higher vibration, localized in a narrow area, spreading slightly outward as a wave packet. The packet carries a specific amount of energy, a specific momentum, a specific spin. Those numbers match exactly what physicists have always called the properties of an electron. The wave packet is the electron. This picture cleans up many old puzzles. Why do electrons come in whole numbers? Why is there never half an electron or 3/4 of one? because the field can only be excited in discrete whole-sized lumps. A single excitation uses a certain minimum amount of energy, and half that energy is forbidden. The field is in a sense quantized. That word quantum simply means a smallest allowed chunk. Every kind of particle has its own kind of excitation. The photon field can be excited into tones carrying no weight, travelling at the top cosmic speed. The electron field can be excited into tones carrying a small weight, travelling slower, with an electric charge attached. The Higgs field can be excited into a rare tone, the Higgs boson, heavy and short-lived. A wave packet can be narrow or wide. A narrow packet looks more like a point and acts more like a tiny ball. A wide packet is spread out over distances large enough to feel like a full wave. Which one you see depends on how you prod the field. The same electron, prodded differently, can look like either. This is the deep explanation of the wave-particle duality that once puzzled early physicists. An electron is always a wave packet in a field. When prodded gently, the packet's wave-like nature is visible. When prodded sharply, the packet's point-like nature is visible. The old argument about whether electrons are particles or waves turns out to have been the wrong argument entirely. They are vibrations. A team of experimentalists in Paris once managed to make a wave packet hold together long enough to photograph it with a kind of stop-motion technique. They caught images of the packet spreading, rotating and slowly dispersing. In the frames there was no ball, no speck, no point. There was a fuzzy, wobbly shape, rippling like a soft flag in a breeze. This is what every atom is made of. Fuzzy shapes in fields. Zoom out for a moment. You're made of trillions of atoms. Each atom is a nucleus surrounded by standing wave packets on the electron field. Each nucleus is a cluster of wave packets on the quark field, tied together by wave packets on the gluon field, all dragged slightly by the Higgs field. Your whole body is a standing pattern of ripples on invisible oceans. Watch a beach at sunset. Look out at the water. Near the shore, the waves come in and go out, rising and falling in rhythm. Some of them break. Others travel long distances. Then occasionally you see a pattern that does not move. A ripple trapped between two rocks. A circle of vibration around the mouth of a small inlet. A steady shape in the water, even though the water inside the shape is constantly moving. Those are called standing waves. A standing wave is a vibration that stays in one place, even though the stuff it is made of keeps moving. The energy is trapped in a pattern. The shape holds. Every atom is a standing wave. An atom is, at its heart, a proton or a group of protons and neutrons, surrounded by a cloud of electron field ripples. Those electron ripples do not move like planets around a sun. They sit in standing wave shapes, pinned around the nucleus by the electric pull between them. Certain shapes are allowed, others are not. The allowed shapes are what give each chemical element its unique properties, its colour, its reactivity, its song when you heat it. Hydrogen, the lightest element, has a single electron standing wave around a single proton. Sodium burns yellow because the standing waves of its outermost electron allow for a specific kind of jump, emitting yellow light when it drops back. The periodic table of elements in this picture is a catalogue of wave shapes. Zoom in on a proton. Inside, 3 quarks are held together by the colour field, inside a little region. The quarks themselves are standing waves on the quark field. The energy of the colour field, itself sitting in standing wave shapes inside the proton, gives the proton most of its weight. The proton, in turn, is itself a standing wave, a tightly bound pattern of vibrations on multiple fields. Everything larger than a proton is a standing pattern of these patterns. Your muscles are made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are standing waves. Your body, with all its trillions of cells and the chemistry between them, is a huge, slowly changing standing wave pattern on the underlying fields of the cosmos. A star is the same, a giant ball of hydrogen and helium held together by its own gravity. Inside the core, nuclei smash and fuse, emitting photons. Each nucleus is a standing wave cluster. Each photon is a travelling wave packet. The star itself is a gigantic structure of waves, held in shape by gravity and supported by the pressure of trillions of tiny vibrations pushing outward. Even the galaxies. Each star in a galaxy is a wave structure, orbiting around a common centre. The galaxy itself is a slowly rotating shape, a gigantic eddy of wave structures, turning in a way that is, in the grand view, itself a kind of long-period wave around the galactic centre. Follow this far enough, and you arrive at a picture that is surprisingly simple. The universe is built out of vibrations, short vibrations inside atoms, longer vibrations inside stars, slow vibrations inside galaxies, all of them sitting on the underlying fields, all of them standing for a while before the ripples fade. This has one quiet consequence. Everything you love is a song, a sustained chord, playing on the cosmic fields. Every moment of existence is a small part of that chord. Most of the universe, though, is silent. Out in the cold dark, a different field is making a whisper so soft that even light cannot catch it. Right now, as you sit wherever you are, trillions of tiny ghost particles are passing through you every second. They are coming mostly from the sun. A smaller number is coming from dying stars far across the galaxy. A few are coming from the very first moments of the universe, still drifting through space. They pass through your body, through the floor, through the earth itself, and out the other side, leaving no trace. They're called neutrinos. They're ripples on the neutrino field. Neutrinos have almost no weight. They carry no electric charge. They barely interact with anything. A neutrino can fly through a slab of solid lead a full light year thick, and most of the time it will come out the other side unscathed. To catch a neutrino, you have to get lucky. Tremendous numbers of them have to pass through a tremendous volume of detector for even one of them to bump into anything. Detecting them is a strange kind of patient art. Deep in a mine in South Dakota, more than a mile underground, scientists have built giant tanks filled with thousands of gallons of a special liquid. The rock above shields the tanks from cosmic rays. Every once in a while, a neutrino from the sun or from a distant galaxy collides with an atom inside the liquid and produces a tiny flash of light. Cameras around the tank catch the flash, a single event every hour or two. Over years, those faint flashes build up into maps of where the neutrinos are coming from. In Japan, an even larger detector sits inside a mountain in an old zinc mine. Its tank holds 50,000 tons of pure water, watched by over 10,000 light-sensitive bulbs lining the walls. The builders painted the inside black to reduce reflections. The detector is so sensitive that it caught neutrinos from a supernova that exploded in a nearby galaxy in 1987. The star was 170,000 light-years away. The neutrinos arrived about 3 hours before the visible light from the same explosion, because neutrinos, being ghostly and interaction-shy, zipped through the outer layers of the dying star while the light had to fight its way out. A whole branch of astronomy now uses neutrinos as messengers. Even stranger, neutrinos come in 3 different types, called flavors. They can change flavor as they travel. A neutrino born as one type in the Sun may arrive on Earth as a different type. This discovery surprised physicists deeply because it required neutrinos to have at least a tiny weight, even though older theories treated them as weightless. The fact that they can change flavor at all is evidence that the three kinds of neutrino fields are tangled together in a way scientists are still actively mapping. Something deeper is also possible. Neutrinos might be their own antiparticles. Every other matter particle has a distinct antimatter mirror. If neutrinos are their own mirrors, it opens up radical new physics, possibly explaining why the early universe ended up with more matter than antimatter. Experiments around the world are currently hunting for the signature of this self-mirror behavior. Each of these ghost particles is a ripple on yet another invisible field, woven through the same cubic inch of space that already holds every other field. The number of oceans in every corner of the universe keeps growing. Those oceans, strange as they are, also allow pairs of distant ripples to behave as if they were one thing. Take a pair of gloves and put them into two identical boxes. Without looking, mix the boxes up. Ship one box to Tokyo and keep the other in New York. When the Tokyo box is opened, the glove inside turns out to be the right-handed one. Instantly, the box in New York must contain the left-handed glove. The two are correlated. You did not need any spooky communication to explain that. The pair was set up from the start. In quantum physics, correlations like that exist, but they have a strange twist. The gloves are not pre-packed. Each box, before being opened, holds a genuine mixture of possibilities. Only when one is opened does the glove inside pick a hand, and somehow, in a way the old glove story cannot explain, the other box instantly has the opposite glove, no matter how far apart they are. That is quantum entanglement. Entanglement is a property of ripples in fields. When two ripples are born from the same event in a special way, their fates become linked. A pair of photons created together can share an entangled state. A pair of electrons, even larger objects in careful conditions, once linked, measuring a property of one instantly sets the corresponding property of the other, even if they have travelled to opposite ends of a galaxy. Einstein famously disliked this idea. He called it spooky action at a distance. He spent years trying to prove that there must be some hidden information preloaded into the ripples, like the pre-packed gloves, to explain the correlation without invoking any instantaneous handshake. Decades after his death, experiments proved him wrong. An Irish physicist named John Bell figured out in the 1960s a clever test that could distinguish between Einstein's pre-packed story and the true quantum story. Different experimental setups would give different statistical patterns depending on which view was correct. Teams around the world carried out the test, first in France, then in Austria, then in China, then in many other places. Every time the results agreed with quantum field theory and disagreed with Einstein. In 2022, the Nobel Prize was awarded to 3 physicists who had pioneered the most rigorous versions of these tests. Entanglement does not allow signaling faster than light. Measuring your entangled particle gives you a random result, not a message. Only when the other person tells you by a slower-than-light phone call what they measured, do the two of you realize the correlations. From the outside, no faster-than-light information has been sent. From the inside, however, a handshake that sits across the cosmos is at work. Modern laboratories use entanglement in real devices. Secure quantum communication networks, first tested in Vienna, then in Beijing, rely on entangled photons to detect any eavesdropper. Because measurement always disturbs entangled states, any attempt to intercept the signal leaves a fingerprint. A spy on a quantum line cannot hide. On a deeper level, entanglement hints at something structural about fields. The ripples on a field are not independent little things. They can be woven together across enormous distances into single patterns. The thingness of a particle is in some sense a fiction. Underneath, there is just one field, and certain ripples on it share their identity. A radical theory born in the last few decades suggests that every piece of three-dimensional reality might be a shadow cast by entangled fields on a faraway edge of the universe. A hologram is a flat piece of film that, when lit correctly, produces a three-dimensional image floating in the air above it. The image looks solid. You can walk around it. You can see it from different angles. The depth, the shape, the sense of volume, all of that is encoded on a two-dimensional surface. The world you perceive above the film is a projection of the information printed on the flat sheet below. In the last few decades, a growing number of physicists have begun to suspect the entire universe might work the same way. The idea is called the holographic principle. The claim is that everything happening inside a volume of space can be fully described by information living on the surface that surrounds that volume. Not a compressed summary, the full, complete story. Every particle, every interaction, every event inside the room is encoded on the walls of the room in a different language, perfectly equivalent. This is not a metaphor. It is a mathematical proposal, backed by decades of theoretical work, starting in the 1970s and deepened in the 1990s by an Argentinian physicist named Juan Maldacena. He showed that in certain carefully chosen universes, a theory of gravity in the interior volume is mathematically identical to a theory of quantum fields on the boundary surface. Two very different-looking theories turned out to be exactly the same physics, written in different notation. The result is called the holographic duality. Even the harshest critics could not find a flaw in the math. Further tests, over the last 25 years, have deepened it. Predictions made on the boundary match events in the interior, and vice versa. The implications are staggering. If the principle applies to our own universe, then what we experience as three-dimensional reality is a kind of projection. The deeper truth would live on a lower dimensional surface, somewhere at the edge of space. Every event you can think of, every cloud, every thought, every footprint, corresponds to an arrangement of fields on that distant boundary. The boundary is the book. Our three-dimensional world is the reading. An image often used to explain this goes as follows. Imagine a flat sheet of paper covered in tiny symbols. You cannot, by looking at the paper alone, see a person. Feed the paper into a special projector, though, and a three-dimensional figure stands up from it, complete with expressions, motion, and depth. Every movement of the figure is, underneath, a rearrangement of symbols on the paper. Physicists studying black holes were the ones who first suspected this might be a deep truth. When a black hole evaporates, the information about what fell in does not vanish. It is encoded on the horizon surface, the edge of the black hole. A black hole behaves like a hologram of its contents. If black holes are holographic, why not the whole universe? Some theorists argue that all of reality is one vast hologram, projected by fields on an outer surface. Every quantum field we've discussed is a feature of that projection. Tests are ongoing. A handful of recent experiments have looked for subtle effects that could reveal a holographic graininess to space-time. No clear signal has been detected. The idea is well supported in simplified theoretical universes and not yet confirmed for our own. A calm version of it still hovers at the cutting edge of physics. Reality might be painted from a flat canvas. Fields might be how the painting shimmers into 3 dimensions, and one field we have not yet discussed is the one that writes the shape of the canvas itself. Every other force in physics has a working quantum field theory. Electromagnetism has one, the weak force has one, the strong force has one. Physicists can calculate with any of them to astounding precision, and the results match experiments. Gravity has resisted every attempt. By analogy, it should be simple. Gravity is a force. A quantum field theory treats forces as ripples on fields, with messengers jumping between particles. If you ask what the quantum field theory of gravity ought to look like, the natural guess is a field whose ripples are little particles called gravitons. A graviton would carry the gravitational force from one object to another, the way a photon carries the electromagnetic force. The problem is that when you start doing calculations with this picture, everything breaks down. The equations begin to produce infinities. Real, unphysical, unbounded infinities that do not cancel out. In other quantum field theories, the same kind of infinities can be tamed by a technique called renormalization, where well-defined rules absorb the infinities into a finite number of physical quantities. For gravity, renormalization fails. New infinities appear at every level of precision, needing fresh fudge factors over and over. The theory loses predictive power. At low energies, things still work fine. Ordinary gravity, the kind you feel pulling you toward the floor, is perfectly described by Einstein's older theory of general relativity. That theory treats gravity not as a force, but as a curvature of space and time itself. Planets orbit the Sun because the Sun warps the fabric of space-time around it, and objects follow the straightest lines they can through the warped geometry. At extreme energies and tiny distances, the classical picture breaks. The rules of quantum mechanics must take over. A black hole center, the first instance of the Big Bang, the edge of a quantum event that also curves space-time noticeably. In these settings, a full quantum theory of gravity is needed, and nobody has one that everyone trusts. This is the single biggest open problem in theoretical physics. Many candidates have been proposed. Some try to treat space-time itself as a field whose ripples are gravitons, while clever mathematical tricks handle the infinities. Others propose that space-time is made of tiny, discrete pieces, like pixels, and the smooth-looking world is just the coarse view. Others say the whole approach is wrong, and gravity is an emergent effect of something deeper, not a fundamental force at all. A handful of physicists scattered around the world have spent entire careers chasing a quantum theory of gravity without success. Some have said that gravity is the field that broke physics. Experiments are brutally hard. To test a quantum theory of gravity directly, physicists would need to probe lengths much, much smaller than any particle collider can reach. The energy required would be astronomically beyond anything achievable on Earth. Some proposals look for subtle side effects in the sky, in the way early universe light patterns ripple. Others use precision measurements of tiny gravitational fields between small masses, cooled to nearly absolute zero in careful chambers. A handful of recent experiments have tried to show that even tiny masses can be put into quantum superpositions, which, if confirmed at larger scales, would prove that gravity itself must obey quantum rules. Early results are suggestive but incomplete. The search for a field that describes the shape of reality itself is, right now, the loneliest and hardest frontier. Two main ideas are trying to cross it. The first imagines space itself as a woven mesh of tiny loops. Picture a perfectly smooth table, run a finger across it, The surface feels uninterrupted. Zoom in with a microscope, though, and the smoothness breaks. You see individual grains, tiny scratches, clusters of atoms. The apparent smoothness was an illusion from far away. One branch of modern physics suggests that space itself might work the same way. At the scale of everyday life, space looks smooth. At the scale of atoms, space still looks smooth, at least in terms of position. Go deeper, however, to a length about 100 billion times smaller than a proton, and space might dissolve into a woven structure. A network of tiny connected loops, each loop carrying a small unit of area, each connection a small unit of volume. The smoothness would be an emergent property of the weave, visible only from afar. This picture is called loop quantum gravity. It was developed starting in the late 1980s by physicists working in Europe and North America. The core idea is to treat space itself as the field, and to quantize that field directly, rather than trying to put gravity on top of a smooth background. If the theory is correct, there is a smallest possible area in the universe, a smallest possible volume. Below that size, space does not exist in the usual sense. There is no smaller or bigger inside the smallest unit. The mesh is all there is. Loop quantum gravity predicts that space is finitely divisible. A room the size of a bedroom would contain roughly 10 to the power of 105 of these smallest units. An enormous number by any standard, yet still finite. Reality becomes, at its deepest level, countable. The loops of the theory come with detailed rules. They can join, split, and form patterns called spin networks. A spin network is a kind of blueprint for a tiny region of space. It tells you the possible ways that space can be connected at that scale. Different spin network arrangements correspond to different geometries. Smooth space on the large scale would be a particular kind of average over many spin networks on the small scale. The theory has successes. It handles, in an elegant way, some infinities that broke the old graviton picture. It predicts that time itself may also be quantized with the smallest possible tick. It produces interesting results about black holes. Some loop quantum gravity calculations agree with known formulas for black hole entropy, first derived using completely different methods. There are costs. The theory does not yet match up cleanly with the rest of the standard model of particle physics. It is not clear how ordinary matter, ordinary photons, ordinary electrons fit into the loopy mesh. Some researchers see this as a sign that the theory is deep and needs more work. Others see it as a sign that it has fundamental issues. A handful of experimental proposals try to look for signatures of a grainy spacetime. The idea is that if space has smallest units, then very high-energy photons travelling across vast distances should show tiny delays or distortions, depending on their colour. Instruments watching gamma-ray bursts from distant galaxies have tried to spot these effects. So far, no clear signal has been found. The smoothness of space at our best measurements is still unbroken. Loop quantum gravity is an open invitation for the universe to be made of a weave. And another older family of ideas says the weave itself is made of strings. A single violin string pulled tight between 2 points can produce many different notes depending on how fast it vibrates. A low, slow vibration gives a deep hum. A quick, tight vibration gives a high whine. The same piece of string played differently creates different sounds. A young physicist in the late 1960s asked a strange question. What if every kind of particle in the universe is a different note on a single, microscopically tiny string? That idea became string theory. In this picture, the fundamental objects of nature are not zero-dimensional points, but one-dimensional strings. Each string is unimaginably small, about 100 billion times smaller than a proton. A string can vibrate in many different patterns. Each distinct vibration pattern corresponds to a different kind of particle. One vibration is an electron, another is a quark, another is a photon, another, notably, is a graviton. String theory, if it works, unifies gravity with the other forces. It also predicts extra dimensions of space. Beyond the usual 3 dimensions you feel around you, string theory requires 6 or 7 more. Those extra dimensions are, according to the theory, curled up so small that they are invisible to us, the way the inside of a garden hose looks like a line from far away, but contains a loop when you zoom in. Each point in everyday space would, in this picture, actually be a tiny curled up shape with more directions inside it. The idea is bold, beautiful, and famously hard to test. For several decades, string theory dominated a large part of theoretical physics. Thousands of papers were written. Whole careers were built around its possibilities. Many of the deepest mathematical results of the last 30 years, including the holographic duality mentioned earlier, emerged from string theory research. There are difficulties. The theory is consistent in its mathematics only in a specific number of dimensions, 10 or 11 depending on the version. Our universe looks like it has 4 dimensions, so string theorists must explain how the extra ones get curled away. Worse, there are an enormous number of possible ways to curl them. Different choices produce different laws of physics. Recent estimates suggest a vast landscape of allowed versions, more than anyone can fully catalogue, each corresponding to a slightly different possible universe. Skeptics have argued this makes the theory unfalsifiable. If it can produce almost any outcome, then it predicts nothing in particular. Defenders argue that the math is so tight in other ways that it must be pointing somewhere real, and that more work will narrow the landscape. Experimentally, string theory has not yet produced a clear, unique prediction that can be checked in a laboratory. Some experimental groups look for subtle signatures, such as extra dimensions showing up in collider data, or unexpected patterns in cosmic signals. No direct evidence has appeared. So far, the best experiments have simply ruled out some of the simpler versions of the theory. In the last few years, string theorists have begun collaborating more closely with mathematicians, cosmologists, and holographic researchers. Some surprising internal consistency results have tightened the theory significantly. Others have revealed that certain simple versions of string theory probably cannot describe our universe. A beautifully vibrating thread of an idea, possibly the deepest picture ever proposed, possibly, as critics argue, a mirage. Whatever wins in the end, there is still the hardest question of all waiting. Why is it that the act of looking seems to force a field to make up its mind? Back to the double-slit experiment from early in this journey. An electron fired alone at a wall with 2 slits rippled through both, interfered with itself, and produced a wave pattern on the back wall. When a detector was added to one slit, quietly watching, the ripple vanished, and the electron behaved like a ball. A smooth, spread-out field became a single localized thing, simply because someone decided to look. This is called the measurement problem, and after almost 100 years of quantum physics, nobody has a fully agreed-upon explanation for it. The issue is sharp. The equations of quantum field theory describe fields evolving smoothly. Given a starting condition, the equations predict how the field ripples change over time. Everything is deterministic in that sense. The math moves forward in calm, continuous steps. Measurement breaks that calm. When a detector records an event, the spread-out field appears to snap into one of many possible outcomes, with certain probabilities for each. One specific dot on the screen, not a pattern. One specific path, not many. The snap is not described by the smooth equations. It appears to come from nowhere, happen instantly, and leave no trail in the math. Physicists have offered several interpretations. None is proven. The first is the Copenhagen view, named after a famous school of physics in Denmark. It says that measurement is a special process. The field behaves as a ripple until measured. Once measured, the ripple collapses into one outcome, chosen randomly with quantum probabilities. The collapse is not explained. It is simply accepted as a feature of nature. Most working physicists use this view in practice, partly because the math works whether or not the collapse has a deeper explanation. The second is the many worlds view, proposed by an American physicist named Hugh Everett in the 1950s. He argued that there is no collapse. Every possible outcome actually happens, each in its own branch of reality. Every measurement splits the universe into a set of parallel copies, one for each possible result. You, the observer, go down one branch. In others, there is another copy of you in a slightly different branch, seeing a different result. The universe, in this view, is a vast tree of branching realities. The third is the decoherence view. It says that when a field interacts with a large environment, the spread-out ripple behavior rapidly becomes entangled with so many other fields that the wave-like interference pattern effectively smears away. The field stops acting wave-like because its wave-like features have been quickly scattered into the environment. No sharp collapse, just a rapid loss of coherence. Many of the predictions of the old Copenhagen view can be recovered from this, without mystical collapse. Still, the question of why a single outcome is perceived, rather than a blurred superposition, remains partly unresolved. Recent experiments have chipped away at some interpretations. Researchers in Austria and China have carried out tests that rule out classes of hidden variable theories, tightening the corner even further. Others have shown that interference patterns can survive much longer than once thought when the environment is carefully controlled. The honest state of the field is this: the math is beautifully clear. The interpretation is still foggy. The act of watching somehow shapes what is seen. Every theory of reality has to deal with this riddle, and none of them do it fully. Against that long-standing fog, the most recent experiments have pushed through in a way that finally settles one old question and opens a new door. Over the last 2 years, a quiet shift has taken place across physics laboratories worldwide. Results from several major experiments have converged in a way that makes one old picture of reality clearly untenable, and another picture, long suspected, clearly correct. At the European Laboratory in Geneva, the Large Collider restarted at higher energies than ever. New runs mapped the Higgs boson with unprecedented detail. Measurements of its behavior, when combined with precision studies of the top quark, showed a strong hint that the Higgs field has exactly the shape predicted by the simplest version of the theory. Earlier, there had been tiny wiggles in the data suggesting possible new physics. After long runs, most of those wiggles faded. A few stubborn ones remain, however, and are under close scrutiny. At a laboratory in Illinois, a multi-year effort measured the magnetic behavior of the muon, a heavier cousin of the electron, down to a level of precision that pinned the anomaly to within the tightest bounds yet. New lattice simulations, running on some of the fastest computers in the world, gave a clean prediction from the pure theory. When the experimental number and the simulated prediction were finally compared side by side, After years of careful checking, a small mismatch remained. Modest, but stubborn. Strong enough to suggest that the standard picture of the fields is incomplete at some level, and something new, not yet discovered, might be lurking as a virtual particle in the vacuum. At astronomy sites around the world, ultra-sensitive telescopes map the faint leftover light from the very early universe in finer detail than ever before. Those maps are sensitive to how gravity behaves over enormous distances. The newest results show no sign of breakdown in the current picture of how fields shape the young cosmos, but they do show small anomalies in the pattern of cosmic expansion that cannot yet be fully explained. Something in the field of dark energy, or in the gravitational field itself, or both, is behaving slightly unexpectedly. In quantum laboratories, new tabletop experiments began to place tiny masses, trapped and cooled, into measurably quantum states. The goal is to see whether the gravitational field between two such masses behaves in a quantum way. Early results, preliminary and still being verified, seem to suggest that gravity does obey quantum rules after all. If confirmed, it would be the first direct laboratory evidence for the quantum nature of gravity. Putting the pieces together, a new picture of reality emerges. Every corner of space is filled with a layered set of invisible oceans. Each ocean trembles at the lowest level nature allows. Particles are ripples on these oceans, and the oceans themselves are connected, layered, and occasionally entangled across vast distances. The Higgs ocean gives weight. The color ocean binds quarks. The weak ocean changes identities. The photon ocean carries light. The neutrino ocean whispers through everything. Gravity, once thought to be a separate player, seems finally to be joining the field family. The old picture of solid balls flying through empty space is finished. So is the slightly newer picture of particles as the most fundamental things. The new picture has fields all the way down, and maybe even fields made of still deeper structures, whether loops, strings, or holographic shadows. You are a pattern, standing on invisible water for a little while. The water will go on long after the pattern has faded. That is what a quantum field really is, and that is enough for tonight. Rest well.